Hello everyone. This video I will talk about how to write subroutines in MIPS assembly code, and we will go through some basic concepts about the main routine, subroutine, caller, callee definitions, and we'll also look at some assembly code examples. So you will need to check the other video about the coding examples for your next lab. And the lab 4 will be about write a subroutine in MIPS assembly code. So this week we need to cover everything about subroutine. So you need to watch both of the videos to understand about subroutine, both in concept and the assembly code. So first of all, we have talked about the memory map, MIPS memory map last time, if you still remember. This is the structure of the MIPS memory. So there's basically 1, 2, 3, 4 parts of the MIPS memory. And we do have the one part is called dynamic data, and one is called static data, one is called the text segment, and the other part is reserved for the operating system. A special part is the dynamic data, which includes both the stack usage and the dynamic data usage. So the stack is growing from the top to bottom, and the dynamic data is growing from bottom to top. So this is how we use this piece of memory differently. So that's why you could have stack usage and the local variables. And we went through the concepts last time for static data, dynamic data, and stack segment. So this number will be a little bit different in our assembly simulator, in our assembly code simulator. Hope you could pay some attention to this number. So check it out what we have in our Mars simulator. So we do have a stack segment in our Mars simulator, but the starting address of our Mars simulator is not 7FFFFFC. So it's a little bit different with this, but still we have a relatively high address used as the top address of the stack segment. So the static data basically refers to global variables. The dynamic data, like all the local variables we were using before, like integer x, integer y inside of your function, and then the basic calculations, the related variables, they are all considered to be dynamic data because they're local visible to your current subroutine or current main routine, but they should not, I mean, they do not need to be accessible or visible to the other routines, the other functions. So we basically don't need to define them as a global variable. Unless you want to define something as a global, then that means you might have different files, different routines, and you could will in your Mars simulator, maybe you have quite a few assembly code, and each of them is saved in a separate file. And at that time, if you want something to be visible, not only the function, but also like variables to be visible to all the different program files, then we could declare them to be global using the .global directive. And then we want to look at how to use the stack. So just as the name, so the stack has a really important feature. We call it last in, first out. Just like you're stacking a few of the dirty dishes, so the dirty plates, then you could not take the plate that you put on the first location. So as this funny figure. So if I stack something here, something here, something here, something here, and then I can only take the place I stacked at the last order first out. And I have to take this out first, take this out, take this out, and then take this out. So there's no way for me to take the plates I stacked on this big group first, because it is actually pushed down to the lower location of the whole queue, of the whole line. The benefit of using the stack memory is you could use less memory when the space is no longer needed. So suppose this is the stack memory, and then I could actually allocate one space when I need one space, allocate two space when I need two space, allocate three space when I need three space. Suppose I need three space, and then I want to put apple on the first location, banana at the second location, orange at the third location. So then I could actually release the three location after finish my usage, right? So if you need 4 different things, then you will not allocate 3 space. Then you will need to allocate 4 space. So that basically means you know how much space you want before you use them. Suppose I need 4 space, then it will be something like this. So I need to take 4 space from my current stack, and I can put my apple, which is my first items I want to store in the stack, and I can put banana at the second location, and I can put orange on the third location, and I can put strawberry at the fourth location. And before I use them, actually, I already know I need 1, 2, 3, 4 different 4 pieces of memory, four locations in the memory. And after I finish the usage of all the things, then I could erase them, or I could actually tell other people I don't need those space, so anybody else could use them. So I can erase this. And this is in general how the stack work. Why we call it first in, last out? Because originally there's nobody using the stack, and then there should be a pointer, stack pointer. So the stack pointer is basically pointing to the top of the stack. And when anybody wants considering to use the stack, then they could basically check the value of the stack pointer. And suppose it is pointing to the top, that means nobody is using any space inside of the stack. And suppose the stack pointer points to this location, that means the first 4 spaces were already taken by someone. So we can now use the first 4 spaces, but the 5th, the 6th, the 7th, all the other locations below that could be used. So we're always growing down. And for example, Feng want to take the first 4 location, because I want to store my apple, orange, strawberry, and banana. And then Feng 2, which is another person, want to take another 3 spaces. So then I will have to move my stack pointer down again. So initially the stack pointer pointing to the top of the stack, and the Feng took 4 spaces, and the stack pointer will point to this location. And after that, Feng 2 want to take some other spaces. She need 3 spaces. So the stack pointer will be decreased again, point to this line. And then once Feng 3 or any other people try to consider or try to look for more spaces in the stack memory, then they could check the value of SP, and they know, oh, okay, SP is currently at this space. If I need more space, then I could push SP down again. So by changing the value of SP, this is kind of like a representation of how much space the stack has been used. And you can always decrease SP's value to allocate more space in the stack. And for example, like after the usage of Feng 2, so like Feng 2 has finished her job and she does not need the 3 space here anymore. So what should she do? Then of course she should move the stack pointer SP back to added by 3 spaces, added by 3 spaces. Then we could view it as this piece, this piece, this piece were erased, were erased. So then if someone else need to use the stack, they can push SP down from my current SP location. Suppose Feng finished her job as well, and then what she should do is move the SP up to the original, because she allocated 4 spaces, 4 pieces of space in the stack, so she should release those 4 spaces in the stack. Then the stack should look like this. So by changing the stack pointer, we have a good track of how much how much space is used in the stack, and we could also let different people or different program to use the stack all together, because we don't need to worry about the other profile, the other files. So the current file only need to understand how much space I need, and I only need to change the stack pointer to allocate more space for myself, and I don't need to worry about the stack pointer point to whatever location at the current time. So we will look at more example to understand this better. And in general, what kind of data should be stored in the stack? So there's basically 3 types of data could be stored in the stack. So local variable, of course, if you need some variables, for example, especially in the subroutine, and if you do have a big array, and then those array are also considered as a local variable, because those array are only existing in one function or in one subroutine. So then why we don't need to store like an integer number or floating point number, like those kind of general variable, local variables, you can use certain registers to hold the value of them. But if you have a huge array, then there's no way for you to put it in the register. So at that time, then we want to use the stack. So this is basically means array, local variables. Like you have a huge array in the subroutine, then we want to store it in a stack. And because we only want to use it in the current program, in the current function, and after the subroutine was finished, then we don't need to use it anymore. So that's why people always want to store it in the stack, because it's a temporary usage. And also, we may have to store certain registers, and they are called the saved register. So we will explain this more using more examples. But certain registers have to be stored if you want to manage the subroutine and the main routine all together. So for example, the main routine might be using register S1, S0, S2, and your subroutine also want to use S1, S1, S0, S2. Then you have to store them, because you don't want to mess up the usage of the main routine, as you have different routines, different program files running at the same time. So you don't want to mess up the other files. So you have to store them in the stack as a temporary storage. Keep the old value somewhere in the stack, and then restore them after you finish your current job. Restore them after you finish your current job. So the third part is called arguments. Third part is called arguments. So arguments is the same concepts we use in any your high-level programming language. So if you have a function call, then you need to pass the arguments, or we could call them parameters. And those value, if you have a lot of arguments, and we have to store some of them in the stack. because there's no way for us to store everything in the register. So we will look at more example, then you will have bit better idea about how what is the argument storage in the stack, what is the register storage in the stack, what is the local variable storage in the stack. So this is the first example we want to introduce. So the left part is the C code and the right part is the MIPS assembly code. So if you still remember, we have introduced the jumping instructions. There are a couple variations of jumping instructions. So the very first jumping instruction is called J label, if you still remember. So it's simply J label. And the second jumping instruction we have introduced is called JAL. And the third one is called JR. So JAL and JR, they're basically JAL and JR, they're basically two different variations of the jumping instruction. Let's look at some example to fully understand. So the JAL means jump and link, and the JR means jump according to the register value RA. And for no matter for J or JL or JR, then we always need to answer a question where we want to jump to. So the meaning of JL is we would like to jump to the label address. We want to jump to the label address. So next instruction get executed will be set according to the label value. Will be set according to the label value. And if you forgot how the address was calculated, you could check the previous slide when we talk about the jumping instructions. So JAL will set the return address. JAL will set the jump address, the target address, according to the label value. Here we have a label called simple. We have a label called simple. So the JAL will set the PC value to be the address of the simple, But before the PC was updated to this value, then there's another important thing was implemented at the same time. It will put PC plus 4, which is the current address PC plus 4. That will be this line. Right? So the current PC plus 4, it is the next line instruction after the JL. It is the instruction after the JL, the next line here, the address of the next instruction after PL. So the PC plus 4 will be stored into RA. And RA is usually called the return address register. It is used to hold the return address all the time. When you have a return, that basically refers to subroutine function call. So what does that mean? So before I jump out to a subroutine, and I want to remember where I was before I make a jump. Before I jump out to any subroutine, I want to remember where I was. So assume I will go out from this line and then finish some subroutine function. And then I have to come back again. But how can I come back? Then I have to remember where I were before I jump out. So if this line is my main routine, then I have to remember my current address, or the address of the next instruction, so that it is called PC plus 4. And if I could remember that, then I can jump out according to the label. according to the label value, So I can first remember the return address, which is my current PC plus 4, and store it in RA, and then make a jump and finish my subroutine, But at the end of the subroutine, I have to return back to my original routine, the main routine. At the end of the subroutine, I have to return to the original main routine. How can I return? Then the program, the CPU will just check the RA return address. So using the instruction JR, so we could jump back according to the address in RA, So that means if you want to use JR, then you have to have the return address in RA. So I have to have a JAL before I use JR. And then usually the JAL is used in the main routine, And the JR is used in the subroutine, So the JAL will have to store the return value in RA, and in the subroutine, by the end of the subroutine, JR will jump back. JR will help us jump back according to the address inside of RA, So this is the basic structure of the function call in your high-level code. And we call it sub-procedure or subroutine in the MIPS assembly code, So let me make a new slide to represent the whole structure. So the main routine is executed according to the PC value. And suppose my current PC value point to this location, point to certain address, and the next line of my main routine, will be PC plus 4. However, my current instruction is trying to call a subfunction. So there will be one subfunction being executed, and that subfunction is stored somewhere else. And how we could find the subfunction according to the label of the subfunction, So before we jump to the subfunction, of course, we should have the last instruction here is actually JAL, jump and link, because we need to store the PC plus 4 into RA. So before the function call, before the function call was executed, before the subroutine was executed, then the RA is already updated by PC plus 4. And then we just need to perform whatever instruction included in the subroutine. And the last step of the subroutine is always JRRA. So that basically means return. So how can we return to the main routine? Because the RA was already updated by PC plus 4, which is the next line after you jump out, the next line after JAL. So then JR $RA will help us to return to the main routine, And the very first example for sub-procedure subroutine MIPS assembly code is really simple, because when you check the C code here, then we actually have nothing performed in the subroutine. So the subroutine here is basically perform nothing except return to the main routine. So everything we did here is basically make a function call. So this is the function call. And then inside of the function call, we only did one thing, which is return to the main routine. So in the subroutine here, then we only have one instruction because we don't need to do any calculation. So the only thing we need to do is return to the main routine. That's why we have only one instruction. Well, we have only one instruction following the label simple here, following the label simple here. And the main routine is, the main routine started after the main label, So in the main routine, we only need to perform a function call, and then we need to perform an addition. So there's basically two things in the main routine. One is a function call, one is an addition. So we first performed jump to the subroutine. So that's the function call here, JL. And then after the function call was returned, then the next step is only an addition. So this is the addition. So in the main routine, there's only two instructions. In the subroutine, there's only one instruction. Well, this is of course not always the real case. In the real case, then you always have to, you almost always have to do like parameter transmission or transmit the argument, because you need to perform certain calculation in your subroutine. So what does that mean? For example, we have this simple function. So the simple function here performs the addition, which is a plus b. And then how can we perform a plus b? Then we have to have input parameter a, input parameter b. So integer a, integer b. In order to transfer the parameters, we have to follow the convention of the maze. And if you still remember, that's like last lecture we have talked about the special usage for all the different registers. And the A group here, they are defined as function arguments. So that means when we want to perform arguments transmission, then we need to put the value into A0, A1, A2, A3. A0, A1, A2, A3. They are specially designed to hold the value. They're specially designed to hold the value of the function parameters. And then if you have function parameter, input parameter, then you have output, return values. So the return value of the sub-function or the subroutine should be stored in V0 and V1, So let's look at the example. Suppose the sub-function is called simple again, and then we would like to perform this simple function using number 10, number 5, So that means we need to transfer two parameters to the sub-function, and the integer main, the integer simple. So the main routine, the simple routine, they can be stored in different files. So this is what you will need to do in your lab. So you have your main routine, you have a subroutine, and they may be stored in different files, assembly code, different assembly files. So how can you compile them together? Then you have to transfer. The input parameter, you have to transfer the output parameter, the output value, return output value. So to transfer the input parameter, then we need to put the first parameter value in A0 and put the second parameter value in $A1. And suppose you have the third one, the fourth one, the fifth one, then they will be stored in A2, A3. A0, A1, A2, A3. So you could store up to four parameters in the A register. You could store up to 4 parameters in the A register. But if you have more registers, if you have more parameters, for example, suppose I have this function. So I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 different parameters. They're all integers. So of course I can put this in A0. I can put this in A1, A2, A3. But how can I handle the other 4 numbers? So that's why we have introduced the usage of the stack. Sometimes you do need to store the argument, which is function input parameters into the stack, So suppose I have another four different values, and all of them need to be stored in the stack. All of them need to be stored in the stack. And when we perform the calculation inside of the subroutine simple, then we just need to take those values from the stack. We just need to take those values from the stack, okay? So we don't have that kind of complex case most of the time. So, but you just need to know, suppose we have really complex, really complex C program, Java program with many parameters, how we could handle that. We could store them in the stack. So here we have only 2 parameters. So the first value is stored in A0, the second value is stored in A1, and then we should be ready to perform the subroutine. So in the assembly code, instead of simply have a JAL simple, then we have to do first initialize A0 with number 10, and then initialize A1 with number 5, because that's the value we want to transfer. That's the value we want to transfer. And after we set A0, A1 to be the correct value, then we are ready to jump to the subroutine. We're ready to jump to the subroutine. So we still use JAL, jump to the subroutine. And inside of the subroutine, then we do not only have a simple return. We do not only have a simple return, because we have to return the value A plus B. We have to return the value A plus B. So compare with the previous example. This one has a simple return. This one has a simple return. And there's no real calculation included in the subroutine. In the second example, we do have a real calculation included in the subroutine. So how can we perform the real calculation in the subroutine? Remember, we want to add A by B and use it as a return value, return that value back to the main routine. So how can we add A by B? Where is my A? Where is my B? Think about that. Where is your A? Where is your B? So the A is stored in A0. The B is stored in A1, because that's the first 2 parameters. That's the 2 arguments. That's the 2 parameter values we want to transfer. And they are stored in A0 and A1. So in the subroutine, then we always assume then my input parameters, they are already stored in A0, A1, A2, A3. So they should be ready for me to use. So I only need to perform ADD. And who should I add? I should add $A0 by $A1. And I should put the result in $V0. I should put the result in $V0. Because by the MIPS convention, the return value of the function should be stored in V0, V1. If you have 2 return values, then you need to use both V0 and V1. If you have 1 single return value, then we only need V0. We only need V0. And of course, you may have multiple values to return. If that's the case, then we still need to take advantage of the stack. If that's the case, we still need to take advantage of the stack to store the whole list of the return value. So for this particular example, so after I add A0 by A1 and store the value in V0, then we should be ready to return, because we have performed everything required in the sub procedure. We just need to perform an addition, and then we should put the return value in the V0, and then we should return back. We should return this value back to the main routine. And then we want to remind you it is pretty tricky here. So the main routine always assume after you return back to the main routine, then the V0 should already have the proper return value. The V0 should already have the proper return value. Because we need to use the return value in the C function, we need to use the return value C and add it by another variable. So we perform another addition using the return value here of the sub function. And this is the addition. This line is the addition. This is the implementation of the addition. So the V0 here is actually the variable C in your C code. The V0 here is actually the variable C in the C code, because the main routine assumes the V0 should be ready. should be ready after I return here. Then the V0 should be ready. So the execution order of all the instruction here. So I do have LI, LI, JAL, ADD, ADD, JR. So the order of the execution order of all the instruction here should be first initialize A0, initialize A1, and then I should jump to the subroutine. So the next instruction being executed is not the ADD here, but the ADD at the beginning of the subroutine, at the beginning of the subroutine. And then the fifth instruction should be JR in the subroutine because we need to return back to the main routine. And the sixth instruction get executed is the ADD after the JAL. It's the ADD after the JL. So this is really important. I hope everyone understands it. The order of those instructions being executed. So we should first execute JAL, and then everything inside of the subroutine get executed after that. And then we should execute the instruction following JAL in the main routine. So this is a perfect example. Try to understand the whole procedure of the subroutine and the main routine. And then, so this page we have briefly introduced the last time. So in order to make any subroutine, then there's the definition of the main routine and the subroutine. They have different names. So the main routine or any routine you could call a subroutine, a subprocedure, a subfunction, then it is called a caller. So the caller calls the subroutine. The caller's job is to set up the arguments before you execute the subroutine and then jump to the subroutine. So exactly here, right? So the subroutine does not need to initialize A0, A1. Instead, we have the main routine to initialize A0 and A1. So that's the responsibility of the main routine to initialize those parameters. And then jump to the subroutine. So the callee, which is the subroutine, is the subroutine that called by the caller. So the callee uses those arguments given to it by the caller and then performs required calculation. After it is done, then the callee will place the return value into V0s, place the return value into $V0, $V1, and then return to the main routine, using JR. So the tricky thing is, well, most of the time, especially in our class, then we do not require you to implement recursive function or multiple function call inside of each other. But you should know that in your C code, Java code, any high-level code, you could have a more complex situation, just like a recursive function. So you might keep calling yourself. Right? So the callee, which is the subroutine, can be sometimes calling another function. So how it will look like? It will look like you have a main routine here. So you might have a main function here. And then we call a subroutine at this location. So I can call this function 1. And inside of function 1, then you call function 2. And inside of function 2, then you call function 3. And your function 3 return to function 2, and your function 2 return to function 1, and your function 1 return to your main routine, right? So you could have multiple function call, of course, multiple level function call. So the main routine here is, of course, a caller because it calls some other routine. And the F1 here is a caller. So F1 here is a caller, and it is also a callee. So we all understand it is a callee. It is a subroutine being called by the main routine. But at the same time, it also serves as a caller because it will call another function, which is F2, right? So the F2 is a callee because it is called by F1. And at the same time, it is also a caller because it also calls F3. So the F3 here is a callee because it is called by F2. And it is not a caller because it doesn't call anybody else, right? So you could have a function serve as a callee and serve as a caller, serve as a callee and serve as a caller at the same time. So the tricky thing here is a callee can be a caller as well. The callee can be a caller as well. The callee can be a caller as well. So the notation of caller and callee are not always clearly divided, but we're just if one function serves as a caller, then the function has to set up the arguments before jump to the subroutine. And if the callee, if one function serves as a callee, if one function serves as a callee, then the callee has the responsibility to put the return value in v0, has the responsibility to put the return value in v0 and jump back to the caller, So we only need to understand the different responsibility. So this is the responsibility of the caller. This is the responsibility of the caller. And this is the responsibility of the callee. So we only need to understand, should I have the V0, A0, A1 is initialized in the main label, under the main label, or should I have the V0 initialized under the simple label? So that's our goal. When they serve as a caller, then they need to get all the parameters ready before you jump to the subfunction. When you serve as a callee, then you need to put the return value into v0. So the different responsibility of the caller and the callee help us to understand how to write MIPS assembly code when we want to perform a subroutine, a function call. So I'll first skip page 19 and 20, and then we will go back to this when we have a really more challenging example. So let's first look at the simple example about subroutine. So how we write a subroutine in MIPS assembly code. So this is a C code example, and we do have a main routine here. So the main function try to perform initialize two variables and then call a subroutine. So that's it. And the sub function, so that's the function we called, is called test. So the test function has two variables in it, two arguments, two parameters, A1, A2. And then using those two variables, we need to perform A1 minus A2 plus 10. So return the value of A1 minus A2 plus 10. So that's the required calculation in a subroutine. So first of all, for any subroutine function call, then suppose we want to finish the assembly code, then we always have a main routine here and the subroutine here. So each defined by a label. And remember, you could have them in separate files. You don't have to, but we will try different settings in Mars simulator, and I will talk more about this in next video. So if you want to save them in the separate files, you could compile and run them together. But if you want to be able to execute all of them, then you have to declare some of it to be global. For example, if I want the test function to be visible to the main function, then I have to set the test label to be global. If I could set the test function to be global, then I should be able to get access to the test subfunction, the subroutine called test, inside of my main routine. Suppose they are stored in different file. So we will talk more detail when we look at the example. First of all, so if I have two different routines, so this is the main routine, this is the subroutine, then I should have different labels, two different labels. And inside of the main routine, I initialize the variables 43 and another variable is number 2. So for example, if I store 43 in a register, then the 2 will be in another register. And then I perform the function call. So I should have a li 43 li2, and then I should perform a function call. And remember, the most important instruction here is the JAL, jump and link, because you want to jump to the subroutine using jump and link, and then you want to return back after the subroutine is finished. So then we have ... just maybe some other instructions here following the test function. So when I use GL, then I should tell where I jump to. So I need to jump to the test label. So I first push the current return address, current PC+4 to RA to return register RA, return address register RA. And at the same time, I need to put the label here. So the JAL performs two things. One is save the return address to RA, and one is move your PC according to the test label, And then how can I initialize 43 and number 2 to a different register? So I should put two different registers here. And then if this is not a sub procedure example, then of course, if you need to use those two values in following calculation, then you can use $S0, $S1. So you can use any regular registers. However, we are actually limited to certain register because we need to perform a function call for the following step. And my X, my Y, they serve as the first parameter, the second parameter of my subroutine. The X and the Y serve as the first and second parameter arguments of the subroutine. So I have to put them into A0 and A1. And then I need to jump to the subroutine. So the main routine has the responsibility to get the parameters ready and store them into the A0, A1, A2, A3 if you need multiple multiple parameters. So inside of this subroutine, then we need to use the input parameters to perform calculation A1 minus A2 plus 10. So that's the only requirement of the subroutine. Then how can I, and then return this, the whole calculations result, So of course, inside of the subroutine, then we always assume the A0, A1 has the first input parameter, has the second input parameter. So I could just directly perform a subtraction using A0, A1, because I should assume when I'm in the subroutine, I should assume this is my first input parameter, which is this one. And this is my second input parameter, which is this one, because they should be already stored in A0, A1. They should be already stored in A0, A1. And after I subtract those two values, I can store it somewhere. Suppose I use T0 to temporarily hold the subtraction result, So what I did here is A1 minus A2, and this is my variable A1, this is my variable A2. Integer, variable A1, variable A2 in a C code. And then I need to subtract this by number 10. I need to add this by number 10. I need to add this by number 10. So how can I add this by 10? So I just need to do ADD $T0 number 10 $T0 done, right? So remember that this is all the calculation I need to perform in my test function, and I need to return this value, which is finally generated in my T0. I should return this value to the main routine. So the main routine always assume after this line, after the function call is performed, then the V0 $v0 should have the return value, So if I don't put the return value in v0, then the main function will have some problems. Suppose later on I want to use the return value. So I have to do here is, well, I have to put my return value, which is currently in t0 into v0, and then I'm done. So the very last step of the subroutine is jump back to the main routine. So how can I jump back? Then I should use JR. And according to the RA value, which is already set by the JAL in the main routine. According to the RA value, then I should be able to jump back to this step. And there's, of course, a simplified version of this. So in the test sub procedure, then I have to do subtraction $A0, $A1. Use the first two parameters to perform subtraction. And at that time, I could actually put the result into V0. And then I can increase my V0 by 10. I could increase my V0 by 10. And then I just need to return, because V0 is the final value already. So I can save one register. T0. I don't have to use it. I don't have to use the T0 here. So I can save one register. This is the solution of this example. And then let's look at another example. Suppose, so this might be something similar to your lab. Suppose you would like to perform a sub-function call, a subroutine, a sub-procedure function call. Then in the subroutine, which is here, the requirement in the subroutine is not really simple. So it does have certain logic condition check inside of the subroutine. So how can we do that? How can we finish this kind of function call? So the main routine is still similar to the previous one. So we have two variables, 43, number 2, and then we need to initialize them, store them in certain register, because the X and the Y, 43 and number 2, they serve as the first and the second input parameters to the sub function. So I need to initialize them to A0 and A1. So I need to put them in A0 and A1. And then the main routine only need to jump to the subroutine using JAL. And inside of the subroutine, after every required calculation are finished, we only need to perform JRRA to return to the original main function, But the calculation required in the subroutine is a little bit more complex than the previous example, because we need to check the input parameters, the two input parameters, if they're equal or not. We need to check the input parameters if they're equal or not. If they're equal, then we need to return the number 1. If they're not equal, then we want to return number 0. So if you try to understand the subroutine requirement here, so we are returning the number 0 if the two parameters they're not same. If the two parameters they are same, then we will return number 1. So how can we do this? Of course, we know how to do function call. The if condition is usually implemented by certain branching condition, right? So for example, we have learned BNEBQ to check if two variables they're equal or not. We have learned BNEBQ to check if two variables they're equal or not. So suppose they are not equal, then we of course want to first initialize my $V0 to be zero. So the very first line of the subroutine maybe we want to initialize the V0 to be 0 because this is trying to initialize the value test, the return value test. And then we need to do the branching instruction to check my first input parameter or second input parameter if they're equal or not. So the branching instruction here basically need to check my $A0, my $A1, because A0 holds my first input parameter and A1 holds my second input parameter. So I need to compare A0, A1. If they're equal, then I want to change my V0 to be number 1. If they're equal, I want to change my V0 to be number 1. If they're not equal, then I only need to jump to the last line. I only need to jump to the last line. So I would like to have another label here called done. And after the done, then we just need to return back to the main routine. And why I use BNE here? Because if they're not equal, then I want to return my current V0. So after I set current V0 to be number 0, then that's my return value. If they're not equal, the first input parameter, second input parameter, if they're not equal, then I will jump to done. I will return to the main routine. If they are equal, then this will not branch. So the next instruction will get executed. So what we should do for the next instruction, then we should change the return value to be number 1 instead of number 0. So we should change the return value to be number 1 instead of number 0. So this is the solution, which is exactly same with the previous page. You could use LI, you could use ADDI to initialize the value of V0. An important part we need to understand, so the main routine and the subroutine, they do have the different responsibility. The main routine need to get the input parameters ready. So it means if you have two input parameter, two input arguments, then you need to put them into A0 and A1, And the subroutine need to perform any calculation required, calculation. But there is always one step, which is the last step is JR$RA, because you anyway need to return back to the main routine. Anyway, you need to return back to the main routine. Also, before you return back to the main routine, then you need to set the V0 to be the return value. All right, so I would like to hold those two harder example. There is one more example here, which is more complex, and it's related to page 19 and page 20. So this is related with how you deal with if sometimes the register used in the subroutine and the main routine, they are same, and how can we avoid messing up everything? So there is certain convention that the main routine should use certain registers and the subroutine should use the other group of registers. And suppose you have to use some register belongs to the main routine or belongs to the subroutine, and you have to save them in the stack. So we will go through those two pages and the very last example here, the very last example in the slide in the next video.